All right, guys, welcome to the second part of our lesson 3 here. Um, so what we're going to be doing today is last time we looked at what continuity is and how to determine continuity by looking at a graph. But today we're going to do the same thing, but instead of looking at a graph, we're going to look at actual like equations instead. So let's go ahead and jump in and see what that looks like.
So now we're going to, instead of looking at this from the perspective of a graph, we're going to look at it now from the perspective of equations. But to do that, we're going to need to look at the second handout that I provided for you guys today. So let's take a look at that. This sheet might be a little overwhelming to look at, but nonetheless, I'll walk you through it. It might help you out a little bit. So on the left side, I'm going to tell you guys the type of functions that we're looking at. So the first one we're going to look at is the polynomials. Polynomials look like this. Basically, like for instance, 5x cubed minus 9x plus 1 is a polynomial. Okay, we work with those a lot in all kinds of math, right? That includes things like linear function, constant functions, quadratics, cubics, etc. All of those are polynomials. Now, polynomial functions, when you graph them, they're always continuous. They never have any holes, gaps, or jumps in them. They wiggle all over the place, but they don't ever have any gaps or jumps. So the interval where they're continuous is from negative infinity to positive infinity. And another way you could say that is they're continuous everywhere. And there are no parts of discontinuity, no points of discontinuity. Talk about exponential functions now. Exponential functions, their equations look like this. It's where the x is in the power spot. When you graph them, they generally have a look that looks something like that. They usually have some kind of a horizontal asymptote down here at the bottom. But notice that there's no, now horizontal asymptotes are okay. It's vertical asymptotes that are a problem for continuity. But as you guys can see, I could put my pencil over here and just trace, and I never have to lift it up as I go to the right. I just keep going. So like polynomials, they're continuous everywhere with no discontinuity. Okay. Now, when we get to rational functions, which you can also think of as quotients, in other words, fractions, we do start getting some discontinuities. Okay, so rational functions very often, they can have holes, but they very often have vertical asymptotes. And so you will end up having some discontinuities with these. So as you can see, the graph was like this, but then I got to pick up my pencil and start over here to make the rest of the graph because there was this vertical asymptote. Anything that makes the denominator equal 0 is a place where there's either going to be a hole or a vertical asymptote. Okay, so let's see. If wherever the denominator, let's talk about I'm sorry, I was reading my own writing. I was a little broken in my brain for a minute there, but anyway, practice. So let's talk about where it's discontinuous first. The function's going to be discontinuous anywhere where the denominator equals 0. Okay, and so where is the function going to be continuous at? Well, let's say that c is the x value that when you plug it in makes the denominator equal 0. Then this would be your interval. So of continuity. So for instance, if I gave you guys this function here, x minus 2, what value of x will make the bottom equal 0? Well, the answer is 2, right? So we have a discontinuity at x equals 2, but it's continuous everywhere else. So anything from negative infinity up to 2, as well as anything from 2 up to infinity. But notice I'm using parentheses, which means that 2 is not included. So basically, this is just a really complicated mathy way of saying it's continuous everywhere except for 2. All right? So that's rational quotients. Now, this should say radical, not radial, so you might want to add a little c in there. But anytime you have an even root, like a square root or a fourth root or a fifth root, their shape often just looks like this. And as you can see, there's really no discontinuities here. It's a continuous line. It's never broken. We won't say it's continuous everywhere, though, because with polynomials and exponential functions, it's literally everywhere. It goes from negative infinity to positive infinity. But for radical functions, they actually have a starting point. and then they're infinite after that. And how you can find that starting point is you just take the radicand, and as you guys know with square roots, the radicand has to be positive, right? So we just let r of x be greater than or equal to 0, and we solve for x. And whatever we get, that tells us the starting point of where it's okay for the function to exist. And that's where it will be continuous. So the function is continuous for all values of x that allow the radicand to come out positive. But there are no points of discontinuity. The graph doesn't even exist behind its starting point, right? So we're not going to call that a point of discontinuity, okay, because it's not a point. That's just the graph doesn't even exist there. But a point of discontinuity is actually one specific location. So radical functions do have a limited range, or I'm sorry, limited domain, so that they are continuous on the domain that they exist on. Radical functions with odd roots, though, actually go both ways forever. And so they're like polynomials. They're continuous everywhere with no discontinuity. Logarithmic functions. Logarithmic functions have vertical asymptotes, and the vertical asymptotes are located where the argument, which I've represented by this function a of x, the vertical asymptotes are located where the argument is equal to 0. So if you want to find out where the function actually starts to exist, you take the argument and you say it has to be greater than 0 because it's got to be positive, and you solve for x. And that'll tell you where the function's continuous at. But once the function started, it never has any holes, gaps, or jumps. There's nothing on this side of the graph, so we're not going to call this vertical asymptote a point of discontinuity. We're just going to call it like the place where the function starts to exist. So sine functions are just little waves, and so are cosine functions. And they're like polynomials. They just exist everywhere. Okay, there's no discontinuities. Now, the other ones, tangent, cosecant, secant, and cotangent, these are what their graphs look like. And as you can see, all 4 of them have vertical asymptotes. And since they're periodic, they just kind of keep going. And they just repeat the same shape over and over and over. That's what trigonometric functions do. They're called periodic functions because they just repeat the same thing over and over different periods. Now, this is a little bit more complicated to understand. But basically, you can find where the vertical asymptote is using this formula. A of x represents what's inside the parentheses. So if you let a of x equal this and solve for x, that will tell you where the vertical asymptotes will be. And those will all be points of discontinuity. If you want to find where it's continuous, it's just going to be everywhere where there are no discontinuities. So it's infinite. It just keeps going. We'll look at some examples of that later today. Same thing applies to all the other ones, but they do have some different formulas. As you can see, tangent and secant have the same formula. Cosecant and cotangent have the same formula, but there's different types there. Another type of function that is really weird in this class that we'll get to a little bit later, just as an extra credit assignment, is something called the greatest integer function, or it's also been known as a step function. But it looks like this, and when you graph it, it looks like a stair step. But basically, you can find all the points of discontinuity anytime the inside of this thing is equal to some integer n. So what do I mean by that? So like, let's say, for instance, that I had 0.5x. Now, what we're going to do is we're going to make it equal an integer. Okay, so we'll take it out of the brackets for now, just follow suit there, and divide both sides by 0.5 when we get x equals 2. And so what that means is that I have a discontinuity x equals 2. Now you might be wondering, where did I get these numbers from? Well, I made this up. I was just calling that my function. But n is an integer, so you could pick any integer you want. I could also pick 2, or I could pick 3, or 4, or 5, or 6, or any of the negative ones also. So basically, if you take your function, which I'm just going to say is 0.5x, and you make it equal any integer you want, and then solve for x, that will tell you a place where there's a discontinuity. It tells you where the stair step stops and goes up to a new spot every time. We'll get to that a little bit later, but for now, just kind of giving you an overview. But as you guys can see in this table, Cn represents a point where the continuity ends, and n represents an integer. So that is the continuity of common functions handout I've given you and how to read it. This is going to be very useful for today's lesson, and we're going to keep coming back to it repeatedly. So let's go back to our notes now, and let's do example 2. So as you guys can see here, I've got 4 problems, and in all 4 of these problems, we're going to identify what type of function it is. We're going to find where it's discontinuous, and then we're going to describe where it is continuous. Okay, so let's go ahead and start off then with number 1. So, let's look at that. I've got something on the top, I've got something on the bottom. Let's go look at our list here of different types of functions. Smaller so it's on the screen. All right, well, what kind of a function is that? Is it a polynomial? No. Is it an exponential? No. Is it a rational? Yes. This is a rational function. So we have our answer to our first question there. It's a rational function. Okay. Next, we want to find out where is it discontinuous. Well, back to the sheet we go. Rational functions are discontinuous when the denominator equals 0. So what I'm going to do then is I'm going to take my denominator, which is x squared minus 9, and I'm going to make it equal 0, and then I'm going to solve for x, and that will tell me where this function is discontinuous at. So first we would add 9 on both sides, and then I would take the square root on both sides. And don't forget, when you take a square root, you always get a plus and a minus answer. So this function actually has 2 discontinuities. It has a discontinuity at 3, and it also has a discontinuity at -3. Now, when you're dealing with rational functions, as we'll talk about a little bit later, those are either going to be wholes or asymptotes. But for now, it doesn't really matter what kind of discontinuity it is. The fact is that since these are the values of x that make the denominator equal 0, these are where the discontinuities are. Now we need to describe the intervals of continuity. So how do we do that? Well, let's start at -infinity first. So we're going to start off at -infinity. And then it's going to be continuous until we get to the first discontinuity, which is at -3. So it's continuous from -infinity all the way up to -3, but then it stops. And then after that, we'll pick up where we left off at -3, and we'll keep going until we get to the next discontinuity, which is +3. And then we'll go from 3. And after that, there's no more discontinuities, so we can just put infinity here. Okay? So this was a rational function. It had discontinuities at 3 and -3 because those are the values that made the denominator equal to 0. And since I know those discontinuities, now I can write out what the intervals of continuity are. Okay? So let me do numbers 2 and 3. I'm going to wait on 4 because that one's a little bit trickier, but we'll do 2 and 3 next. And then I'll let you guys practice a little bit after I finish 1 and 3. Well, let's go ahead and take a look now at number 2. Number 2, what kind of a function is that? I've got a root here symbol with a 3. So let's go back to our little sheet here. It's not a polynomial. It's not an exponential. It's not a rational. It is a radical, but it's not an even root. It's a radical with an odd root. Okay, cool. So we can write that down now. It's a radical function. Now, we want to know where is it discontinuous. So let's go back to our sheet. Radical functions with odd roots. Oh, they don't have any discontinuities. So we're going to say there are none it doesn't apply. There are no discontinuities for radical functions. So where is it continuous at? Let's go back to our sheet. Radical functions with odd roots are continuous everywhere. So we don't have to do any math on that. The answer is it's continuous everywhere. That means no matter what value of x you pick, there will never be any holes, gaps, or jumps anywhere in this function. So radical functions, and I should put odd root. Radical functions with an odd root don't have discontinuities and they're continuous everywhere. Now this is a good time to talk about something like, so why do we do this? Why are we trying to figure this out? Well, like I said in the last half of the lesson, continuity is very important. Every theorem that we use in calculus, almost every theorem requires the function to be continuous. So you can only apply a lot of our math or a lot of our calculus theorems to functions when they are continuous. So it's very important you know where they're continuous and where they're not, because where they're not, you will not be able to apply the theorems, and if you do, you'll actually end up with a wrong answer. So it's important to know where functions are continuous. Let's do one more problem here, number 3. Number 3 is a square root problem. So that is another radical problem, but this time we have an even root because it's a square root. Now let's go back to our little cheat sheet here and see where are the discontinuities for radical roots, the radical functions that have even roots. Well, there are no points of discontinuity, so once again we're going to say none. But in this case, we're not going to say that it's continuous everywhere. Even though there's no holes, gaps, or jumps in this function doesn't exist everywhere. So we could tell that by looking at our little sheet here. As you can see, let me bring it up again. Radical functions, they only exist for all x for which r of x is greater than 0. And r of x represents whatever is underneath of the radical there. So we need to come back over here, and to find out where it's continuous, what we're going to do is we're going to take the radicand, and we're going to say, okay, the radicand has to be greater than or equal to 0. And then I'm going to solve for x. So this function is continuous for all x greater than or equal to -4. Anything less than -4, the function doesn't even exist anymore. And if you were to graph this function, it would look something like this. You don't have to graph it, but I'll just show this to you. If you graphed this function, it would look something like this. So as you guys can see, there's no holes, gaps, or jumps in the line, but the graph starts right here. There's nothing over here on the left side. So there's no points of discontinuity, but it's continuous from -4 on up into infinity. So you can write your answer like this, that's fine. If you wanted to write it in the parenthesis notation style, it starts at -4 and it ends at infinity. And as a matter of fact, 4 is included because it can equal 0, so we can actually put a bracket here. But like I said, this method is fine. You can write it either way. Okay, so I'm going to stop there. You guys I'm going to give you a couple problems to do where you have to tell me what kind of function it is. You have to identify where the discontinuities are, and then you have to describe the intervals of continuity. We're going to wait on the trig ones because the trig ones are slightly trickier. All right, so I'm going to ask you guys to do numbers 1 through 3. Okay, so pause the video here, and when you unpause it, you'll see the solution. Well, actually, let me give you guys a little hint for this one. For this one, you're going to need to factor it first, and then to find where it's discontinuous, you'll set each piece equal to 0. Another way you could solve this one is you can use Quadratic Formula, which is kind of a pain in the butt, honestly. I think it's easier to factor and set each piece equal to 0. But go ahead and do the best you can with these, and then when you unpause it, I will show the solutions. And here's our solutions, you guys. So for number 1, that was a rational function. And if we set the denominator equal to 0, this is supposed to be a 3. You factor it, as I told you. If you factor this, you get x plus 2 times x plus 1. If you don't know how to do that, I will explain it to you when I'm done going over all three of these. But there's the factoring. Then you set each factor equal to 0, x plus 2 equals 0, and x plus 1 equals 0, and solve both. And those are your 2 points of discontinuity. And so if those are your 2 points of discontinuity, there's your interval of continuity. So it would go from negative infinity up to negative 2. And it would go from negative 2 up to negative 1. And then it's going to go from negative 1 up to infinity. Okay. Number 2 was an exponential function. They don't have any discontinuities and they're continuous everywhere. Number 3 was a logarithmic function, which also has no points of discontinuity, but they're not continuous everywhere because they don't exist everywhere. They start at a vertical asymptote, and you can find that by taking the part inside the log, which in this case was the 3x minus 2, making it greater than 0, and solving for x. So if you solve for x here, you would end up with x is greater than 2/3. So the function is continuous for all x greater than 2/3. Another way you could have written this is as not brackets, but you can use parentheses. Now the reason why we would use parentheses is because, like I said, it starts at a vertical asymptote. So the graph doesn't actually equal 2/3. 2/3 is like the imaginary boundary line it can't cross. So we'll put 2/3 as a starting point that it can't touch. Okay. And that's logarithmic functions, exponentials, rationals, polynomials. We've done a whole grip of them. Now let's talk about this though really quick. How do you factor a polynomial? If you guys don't remember that, I'm going to demonstrate that for you here. It's something you're definitely going to need to know. It's going to come up repeatedly in here. So this is a little review lesson for you. So if you don't know how to factor that, let me review that with you now. Okay. The way that you factor is you take the first term and you put it in the top left corner of a 2 by 2 square. And you take the last number and you put it in the bottom right corner of a 2 by 2 square. And what you do is you look for two numbers that multiply to make that number. So what do you multiply together and make x squared? Well, that would be x times x, right? So you're going to put one of those factors here and one of those factors here. Then you're going to do the same thing with the 2. What times what makes 2? Well, that would be 2 times 1. And then you complete the box. So that means we need to know what these two squares are. Those two squares can be found by multiplying this number by this number. That gives me 2x, and that's what goes there. And then for this bottom left-hand square, we do x times 1, just like a Punnett square in biology. We get 1x. Now, the last thing you have to do is you have to check your work. And here's how you check your work. You add these together. 1x plus 2x is 3x. If those two numbers add up to make the middle number, then you've done it right. Okay? Now, the reason why it's important that you check your work is because sometimes with the numbers that they give you, there's more than one possible way to get these numbers on the outside. And so even though you might get one that works, when you add these up, it doesn't give you the middle number. Well, that means you need to try some different numbers. You know, like, so for instance, let's say I had like a 6 here instead. If I had a 6, well, it could be 2 times 3, right? But it could also be 1 times 6. So if your first pair of numbers don't work, try a different pair of numbers. Sometimes it also helps to switch the numbers around. But the point is that you're looking for two numbers that multiply to make x squared, two numbers that multiply together to make 2, and then when you FOIL it out, you should end up with something that makes the middle by adding them together. Okay, and so the final result is this top piece and this bottom piece. Now, if you want, we still have one more problem to do, but before we get into that, if you want a quick factoring practice problem, I'll make one up here for you. Let me think of a problem real quick. How about that one? So see if you guys can factor it. Pause the video, and if you don't want to practice this because you know how to do it, that's awesome. You can just skip this part. But for those of you guys that do want to practice factoring a little bit, I would encourage you to pause the video here and give it a try. Like I said, this is something you guys are going to need to know how to do. It's going to come up again later on. Just a basic Algebra 1 skill, but easily forgotten. Pause the video here, and when you unpause it, you'll see the solution. All right, so here's the solution. X squared goes here, 12 goes here. Now, x squared has only one possibility. It's got to be x times x. But that 12 is a sticky issue. It could be 1 times 12, or it could be 2 times 6, or it could be 3 times 4. Just remember, though, we're trying to get this middle number. The correct choice would have been 3 and 4, because x times 3 gives me 3x, and 4 times x gives me 4x. When I add these together, I get 7. So the correct factorization would be this. All right, and like I said, that's going to come in pretty handy at many points in this class. So let's go back. The last one we're going to look at here is number 4, and it's a trig function. I'm going to let you guys do the sine function, and I'm going to handle the tangent function. So here we go. Let's do the tangent function. Well, obviously this is a tangent function. That doesn't really take much to recognize that. The function itself tells you what it is. All right, let's go ahead and take a look at our little sheet, though. All right, I'm going to change it to the word tangent. That's what I should have put there. But anyway, let's go to our little sheet here and see where is tangent discontinuous. All right, so we're going to find the tangent function. There it is, tangent. And it tells us it's discontinuous for all x for which pi over 2, well, I said that wrong. It's discontinuous for all x for which a of x, which is the part inside the tangent, for which a of x is equal to pi over 2 plus n pi, where n is just some random integer like 1, 2, 3, 4, 5, or -1, -2, -3. So let's go ahead and see how the heck do we work with that situation. So my a of x in this case is pi x. So I'm going to write pi x is equal to pi over 2 plus n pi. Okay? Now, I'm going to solve for x. So what I'm going to do then is I'm going to divide both sides by pi. So I'm going to put divided by pi, divided by pi, and divided by pi. So here the pi cancels, here the pi cancels, and here the pi cancels. Let's see what we're left with there. I'm left with x equals 1 over 2 plus n, where n is an integer. So in other words, this, I'm writing this in the wrong space, by the way, you guys. This is the answer. Let me circle this. This is where the discontinuities are. Let me circle all that. That goes up here. So there are discontinuities anywhere where you have 1/2 plus an integer. So for instance, you don't have to write this part, but I'll just give you a couple of examples. Pick an integer like 1. Well, what's 1 plus 1/2? Well, that would be 1.5, right? Or how about 2? 2.5. Or if you pick 3 for your n, 3 plus 1/2 is 3.5. So any integer with a 0.5 added to it will be a solution that gives us a discontinuity. How about negatives? Let's say I plug in -1. -1 plus 1/2 is -0.5. How about -2? If I plug in -2, -2 plus 1/2 is -1.5. All of these places are places where the tangent function would have a vertical asymptote, and it would be discontinuous at that point. Now, you don't need to write these as your answer because it's infinite. It never stops going. So we write our answer like this. We say the tangent function has a discontinuity at x equals 1/2 plus n, where n is any integer. And that represents all the possible answers. Okay? So how would we describe the intervals of discontinuity? Well, honestly, I'm not even going to ask you a question like that for these. It's kind of stupid. But I'll do it just for the sake of the notes, and you guys can do it too, just for the heck of it on this one. It's not like I'm going to test you on that, and nobody's going to ask you that anyway. you will be asked to identify the points of discontinuity. You do need to know where those vertical asymptotes would be for the tangent function, but the continuity, not so much. So for instance, as we've already established, anywhere where there is a integer plus a half for this one. So I put dot, dot, dot because it means it just keeps going. This pattern repeats for infinity. But I'll just start at negative 1.5 to negative 0.5. It's continuous on that interval. And then from negative 0.5 up to positive 0.5. So I just keep going up by 1 every time. And then from 0.5 to 1.5. And so these are all the places where it's continuous in between each point of discontinuity. So we'll do it this once just to kind of, stretch ourselves a little bit mathematically, but it's not necessary to know how to describe the intervals of continuity for trig functions. But I do want you to know how to find where they're discontinuous. So student practice time. I want you guys to do this one. So pause the video here and see if you can accurately, well, obviously it's a sine function, so that, I'm telling you the answer there. But see if you can accurately identify where it's discontinuous, and also try to describe the intervals of continuity. And when you unpause the video, see the solution. There you go. Sine functions have no discontinuities, so they're continuous everywhere. All right? And that's it, guys. That's the end of that second half of lesson 3.3. You do have a new homework assignment, even though you didn't really have much new notes to turn in, and therefore you're not turning in the notes. As far as the homework goes, though, you do need to do the new homework assignment for this and turn that in. Okay? And we'll see you guys next time for the next lesson.